or not? Should I use the microphone, the back row? Yes or no? Sounds like it sounds like a mixture. So a mixture. We will put these here. Everybody hear me okay now? Usually I don't need it. I don't need a microphone. My voice fills the room. In fact, it's been known to fill the room so completely that the audience leaves to make room for my voice. I wish I could give this talk in Spanish. In fact, Mateo is not a very good teacher. He's been trying to teach me Spanish, except, you know, he grew up. He was born about 45 kilometers from here in a small village called Alphamen. In fact, they named the public school after him a couple of years ago. But, you know, it's been a long time since he's been in Aragon. He went to that other country on the Mediterranean called Catalonia. And so he sometimes teaches me Spanish, he sometimes teaches me Catalan, and I'm so confused that I perhaps had better talk in English, which is the one language that I think I do know. This is my second visit to Zaragoza. It's a pleasure to be able to be the first speaker at CEDI 2007. Due mille sete? No, dos mille. Mille? Mille. Come on, you gotta help me there. Sete. Good. It is a pleasure. My first visit here was to lecture at the university, at Zaragoza University, as a guest of Professor Victor Viñals, and it was Mateo accompanied me. He wanted to make sure I didn't get lost. By the way, he did not mention my #1 award, which, in fact, you have to understand, my #1 award, right? And you don't even mention it. Amigo de Mateo. And we had a delightful day. We first started with the night before with coffee with Mateo and Victor and me. And then a wonderful day, lecture, the energy with the graduate students was fantastic. If I keep on going, then there'll be no time for lecture. So this performance I should really do, this is called tuning up. So this thing, I've never used one of these before. And looks like I won't use one of these today, because so if it goes, no, I can see it. Can you see that red dot? Yeah? I don't know. Normally I use these overheads and I take out my pen and I can point down and it'll show up on the screen. But they convinced me I should use this new invention called PowerPoint, which for me, now let's see. I think what happens is if I do this, it goes on to the next one. Good. So the microprocessor 10 years from now, why it is relevant to all informatics. So I understand that some of you, like me, care about computer architecture, but a lot of you don't. A lot of you are involved in other parts of what I call the transformation hierarchy. We express problems to be solved on the computer in natural language, English, Spanish, French, Catalan, whatever. But the computer can't deal with natural language. There are too many problems with natural language, ambiguity, etc. So we convert the problem from a natural language statement to an algorithm. Get rid of all the uglies. Now we've got it in a precise form. As you all know, an algorithm is what? It's a step-by-step procedure where each step is precisely stated, property of definiteness, is able to be computed, property of effective computability, and will eventually terminate so you can find the answer. From the algorithm, we then write a program in some mechanical language. You know, C, Fortran, COBOL, C++, any other language? That's it? Prolog, Lisp, No. Java is a religion, not a language. And from the program we compile to the instruction set architecture of the machine, which is implemented with a microarchitecture, which is where I come in, where Matteo comes in, where some of you come in, to try to squeeze as much performance out of the whole package to solve the problem much faster using the stuff that's available to us at the microarchitecture level, some of which I will mention in a few minutes. The microarchitecture is built out of circuits, and the circuits provide the voltage potential for the electrons, which really do the work to go from one potential to another and solve the problem. If I was only able to speak electron, I wouldn't need all this nonsense. I could walk up to the computer and I could go, electrons, arrange in order these 1,000 values. The electron is sort, solve the sorting problem. Unfortunately, I can't speak electrons. Electrons can't speak English. And so I'm stuck. English because I would state the problem in English. Some of you might state it in English or Spanish because you are, what's the word? Bilingual. Or some of you might state it in English and Spanish or Catalan because you're trilingual. And if somebody only speaks one language, you call them what? An American, that's right. At each one of these layers you see there, we have historically provided the opportunity for improvement. So we have algorithms, people who work on algorithms. Many of you in informatics are way up at the top describing problems and coming up with algorithms. And anything below that, well, that's not your problem. You just run it. You boot up Windows or Linux and let it run, and you could care less what goes on underneath. And that's been okay up to now. And as the title says, 10 years from now, why it is not going to be okay as we move into the future. Historically, we have all operated this one layer. And the barriers between the layers we haven't broken. So if you work on algorithms, you work on algorithms. If you work on programming languages, if you work on designing a new instruction set architecture, or me, the microarchitect, I work on pipelining and registers, how many registers should be and what kinds of registers, and the branch predictor that Matteo mentioned, and stuff at the microarchitecture layer. And we mostly keep the layers intact. At the lowest level, the electrons, the transistors. I have in my pocket, this turns out to be, so it's a keychain. The reason why we have a keychain here is because Intel, that made the chip, insisted on having 100% yield. And so those chips that were not able to be put into a laptop, they make into keychains. This chip, 1992, so it's not even new. 3.1 million transistors, running at 66 megahertz. That's 1992. It's not the first chip. First chip was what? The Intel 4004 in 1991. 2,300 transistors running at 105 kilohertz. Look at this jump, only 20 years, and we go from 2,300 to 3.1 million. 105 kilohertz to 66 megahertz. Today, more than 1 billion transistors on a chip, running at 3 gigahertz. 10 years from now, we're going to have numbers like this. 100 billion transistors, more than 10 gigahertz. As time has changed and we have more and more transistors on the chip, if we want to keep pace with the performance of those chips so that the software, the informatics person that's writing software doesn't have to worry, can't do it anymore. There are problems that make it so that the informatics person has to worry about what that microarchitecture looks like. Up to now has not been a problem. We've maintained those walls. We've kept the abstraction layers secure, which is kind of good for the person who doesn't want to stretch the brain or have to worry about anything more than just that one thing that is his or her job. In fact, I can say his job. It's a negative, so I can say his when it's a negative, right? It's only, you have to be politically correct when it's his or her, right? When it's good. But when it's not good, you can just say his, yeah. Yeah. So stay within that abstraction layer so that he doesn't have to hurt the brain. Makes for a better comfort zone. Up until now, mostly this enormous improvement in the technology has been to improve the microarchitecture. So the first thing we did was we said, this microarchitecture, you know, you fetch an instruction and you decode it, and then you figure out where the data is, and you get the data, and then you execute the instruction, you store the result, and then you fetch the next instruction. And somebody said, you know, I've been to a factory, you know, why don't we put an assembly line in there? So I fetch the instruction and hand it off. Somebody else is decoding while I fetch the next instruction, hand it off. Somebody else is figuring out where the data is while the second instruction is being decoded, while the third instruction is being fetched. And we have this assembly line on the chip. And if you write software, you don't have to worry about it. But if I have this assembly line, which we call pipelining, I can effectively get the performance of this instruction finishing every cycle, even though it takes many cycles to get through that assembly line. Put caches on the chip, because if you need data and it's not on the chip, then it takes forever. Hundreds of cycles to get information from off the chip to on the chip. You know, years ago people used to worry about decreasing the number of operations on the chip. So instead of doing n multiplies, I'll do n minus 1 multiplies. And I'll save maybe 3 or 4 cycles. Except that the time I waste if I have to go off the chip is the time it would take me to do 100 multiplies. A little bit misguided, if you will. So we put bigger caches on the chip. Branch prediction. So that when this pipeline is processing, you've all written code, so you know what an if statement looks like. An if statement that the ISA layer says if something is true, you go this way, otherwise you go this way. Which means that right after you fetch the instruction, you need to know whether to go this way or that way. Except that the this way or that way is based on the previous instruction that hasn't worked its way through the assembly line yet. So what do? You guess. It's called branch prediction. The better the branch predictor, the better you didn't guess wrong. And if you're going to guess, you may as well process what you've guessed. It's called speculative execution. All that stuff unknown to the layers above, because they don't care. As long as their code or your code executes, why should you care what's going on below? Out of order execution. You write a program, you expect the program to execute in the order that you specify the instructions. Well, tough. I'm a microarchitect. I know I can make it go faster if I do them out of order. So I do. Provided I confirm, commit, let you know what I did only in the order that you specify. So you specify do 1, 2, 3, 4. I can do them in any order I want. But I let you know I've done them in the order 1, 2, 3, 4. Out of order execution. You don't know as a programmer that the processor is executing these instructions out of order. It's okay so long as I build in the structure on the chip in the microarchitecture to give you the same results you would have gotten if they were done in the order that you specified. But because I can do them when they're ready, rather than waiting for the go in sequence, wow, I can get your job done a lot faster. It's kind of like if your instructions 1, 2, 3, 4 are like automobiles traveling along a single lane highway. 1, 2, 3, 4, and they're driving along. And now all of a sudden, the second automobile needs to stop for gas. It's kind of like this second instruction needs to get data off the chip that takes 400 cycles. Now the third instruction, the fourth instruction, or the third automobile and the fourth automobile, they don't need to stop for gas, but because there's only one lane, they sit and they wait until the second automobile gets gas and continues on, and then the third and fourth can continue on. So that the 4 automobiles will arrive in the order that the person organizing this caravan wanted. So we computer architects have a better idea. We say, why don't we do what they do in the highway? If you want gas, you don't stop. You get off the highway to get gas. And then the third and fourth cars go along. And at some point, the fourth car needs gas. He gets off the highway. The third car goes along. Meanwhile, now the second car has got gas, and he goes along. And cars get gas, they get back on. But what doesn't happen is everybody waits for the car that needs gas sitting there in the way. In order execution, the order that the program specifies says you do them one at a time, and if you can't complete, you wait. What we do is we take a page out of the highway manual that says put a gas station off to the side. And then when we finally reach the other end of our trip, this caravan, which perhaps is going from Zaragoza to Barcelona maybe, and just outside of Barcelona, what do? We sit and we wait and we reassemble the cars, and so they enter the city in the order that the caravan person wished. But now, the time that is wasted is the time that you stop for gas, not the time that the multiplicative, the time that everybody stopped for gas. The programmer writing the program in order doesn't know, doesn't care, could care less what's going on underneath, as long as the results finish in the order that the programmer intended. Finish. As long as the cars enter Barcelona in the order that the caravan person wanted to. Trace cache, another element, a structural element to help at the microarchitecture level. It turns out there's a big difference between the order of instructions that the compiler produces, 1, 2, 3, 4, and then a branch. Go this way or go that way. Go this way or no. 6, 7, 8, 9, and then a branch. 11, 12, 13, 14. And so in this on-chip storage, when I go to the storage and say, fetch me a bunch of instructions, let's say I can fetch 8 instructions. And 1, 2, 3, 4, 5, except that the 6th one's over here, 6, 7, and 8. Or maybe I can fetch 16 instructions, 9, 10, and the 11th one is over here. And what I would like to happen is I say, on-chip storage, we call them instruction caches, gimme. We'd like the on-chip storage to say, sure, here. Except I can't do that in one cycle. So what I do is I get 1, 2, 3, 4, 5, and that's it. So where is it written? You know, when Moses came down, if he did come down, I'm still not too clear, but if he did come down, he didn't say, you know, thou shalt not store the instructions in the order that they want to be executed. You have to store them in the order that the compiler produced. I say, no. Let me put on the chip a trace cache, part of the microarchitecture. So even though the compiler produced code where the instructions were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, etc., On the chip, I can package these 5 and then take these and package them here and take these and package them here. And as long as I keep executing them in that same dynamic order, everything's terrific. So up to now, the use of these now 1 billion transistors has been to improve the microarchitecture, and the levels above don't even know it happens. But even now, these levels of improvement in transistors doesn't lead to necessarily a terrific chip. Intel comes up with the Pentium M, the be-all and end-all, designed by the design team in Haifa, Israel, when they're not dodging the Hezbollah missiles that get launched from time to time. Pentium M. And they say, we have chosen these transistors very carefully, and we really have an efficient use of all the transistors. And how many transistors on the chip? 77 million. And how many of those transistors are just being used for a second-level cache, which doesn't pay the bills? In fact, anytime you hear that computer architecture is dead because of the principle of diminishing returns, because of the principle that the benefits to be accrued from these additional transistors isn't worth the additional transistors. Anytime you hear that, you should think back and say, well, why is that? Is it because they don't know how to? Because there's no point in using these transistors, these extra transistors? Or is it that they don't know how to use them effectively? Second-level cache, 50 million of the 77 million transistors are sitting in a second-level cache not paying for itself, because most of the time you're not going to the second-level cache. Most of the time you're working, in fact, that second-level cache, how many values are accessed from that second-level cache in any one cycle? Just an infinitesimal amount of all that storage. Maybe the reason why these second-level, and it's not just the second-level caches consume so much, and it's not just the Intel Pentium M. If you look at the Power 5 chip, half the chip is an L2 cache. You look at the Athlon chip, half the chip is an L2 cache. It's because they got all these transistors, they don't know how to use them effectively. So they just throw L2 cache. So even now, and we haven't reached the 100 billion transistor number yet, but even now, we end up with a poorly utilized chip. Future process technology won't allow us to continue to keep these barriers separate. There'll be too many cores, and too many cores on the chip. Why too many cores? Again, people don't know how to use the transistors effectively. In fact, you think for a second, you see these, now we have what? Dual core, we've got quad core. Niagara has 8 cores. You say, why is that? Well, let's take the Intel example. We have 1 billion transistors on a chip. 1 billion transistors. I don't know how to design with 1 billion transistors. Don't have to. Pentium 4 only takes 50 million. And in 3rd grade, you learn division. 50 goes into 1 billion 20. 50 million goes into 1 billion 20 times. 20 times 50 million is 1 billion. So you say, I know how to design a 1 billion transistor chip. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and I'm done. As we get these many, many cores, we have a bandwidth problem. Each core needs to go off chip some of the time to get information. I once was a consultant on a multi-processor project, NCR, and we had a bus. We had 486s on that bus. It was a good amount of time ago. And so I did the analysis, and I said, one processor on that bus, Snoopy bus even, didn't have to be a right-through bus, Snoopy bus, so it doesn't consume so much bandwidth. I said, processor on the bus, well, 2 processors on the bus. Well, 3 processors. They wanted 4 processors. They wanted 8 processors on the bus. And I said, you put 2 processors on that bus, you're going to saturate the bus. There's not enough bandwidth to satisfy these cores. So the future technology, we're going to go to 100 billion transistors. We have a bandwidth problem. 100 billion transistors, we have a power energy problem. So we're not going to be able to solve this microarchitecture problem to increase performance if we don't engage people at the higher levels, the informatics people in this room who are not interested in computer architecture, but you're going to have to be. Because the answer is we have to break the layers, these barriers between the layers. We've already done it in limited cases. Predication is a good example. Compiler allows predication, the microarchitecture delivers performance. Here's an example. The CX register in the Intel x86 ISA, where if you have a loop and you want to execute that loop so many times, well, if the ISA has a CX register, you can load up that register and you just keep executing the loop, counting down that register. When the register goes to 0, done. So 100% branch predictor on loops. So we've done it in a couple of cases. We've got to do it more. You know, one of the things I get pushed back all the time, you've got to keep these barriers because of this feel-good thing that you can't expect the algorithm person to worry about the microarchitecture. Why not? If I was writing a sorting algorithm and I knew I had thousands of cores, I might do the quick sort, which in the limit is big O of n squared. But if I've got thousands of cores that are running and I can do multiple comparisons at the same time, you know how quick sort works. Your first pass separates all the data into two parts and you can run the second pass in parallel. And the third pass, now you got four things going. If you knew what the microarchitecture was. Pragma's in the language. You know, who better than the programmer knows what's going on? Well, no, pragmas are bad. And so the compiler has to guess what the programmer wanted. The algorithm, the compiler, and the microarchitecture together, if we allow these barriers to be broken. The Alpha 21164, Dick Seitz, who was one of the key architects on the Alpha 21064, the first Alpha chip, was too wide, in order, pretty silly branch predictor. It was their first Alpha chip, and they were going for frequency 200 megahertz, 1992. And then a couple of years later, the 21164 came out, which was 4 wide, still in order, better branch predictor. By then they graduated. Our 2-level predictor was out by then, and Intel was working with it, but digital was still, they graduated to Jim Smith's 2-bit saturating counter. And Dick Seitz ran some experiments and noticed that the chip, which could fetch 4 instructions each cycle, was delivering performance of 1 instruction every 4 cycles. The chip has the ability to do 4 each cycle. It's doing 1 every 4 cycles. 16 to 1. 6% of the efficiency of the chip. And he went in and he looked and what's going on? What's going on? What's going on is you get a cache miss. You wait an enormous amount of time to go off the chip and bring in all this crap, of which you use 5%, and then you do another cache miss, and you throw all this away while you bring in another. What if the algorithm and the compiler and the microarchitecture could work together so that you weren't wasting all this time bringing in stuff that doesn't get used? The refrigerator. So if I've got a huge number of transistors on this chip, maybe I can afford to build large units of functionality that would sit there powered off, and it has to be powered off because we've reached a point with these dimensions where leakage current kills us. That is, the source and drain of the transistor are so close together that I don't have to worry about what the input to this gate is. The electrons will go through the back door. So I got to be able to power off these transistors when they're not being used. But I'm talking about 100 billion transistors. Even today we should be doing this with 1 billion transistors on a chip. You know, Intel had the x86, 8086. How did it do on floating point? It didn't. If it had a floating point instruction, it kicked it to the 8087. Let it do it. 286, kick it to the 287. 386, kick it to the 387. 2 chips. One to do everything, one just to do floating point. Not a dual processor here, just a baby gorilla that could do floating point instructions. How about the 486? Kick it to the 487? No, there was no 487. Why? Because by the time they got to the 486, they had 1 million transistors on the chip, and that was enough to take the floating point unit and put it right on the same chip. Big performance improvement. 1 million. It was enough. We're talking 1 billion today and 100 billion downstream. How about using some of that functionality to do a piece of work, maybe a fast Fourier transform? You don't do it in software, you do it in hardware. Put in the input, zap, and you got it. Be great for DSP chip. One instruction, do fast Fourier transform. Most of the time, you're not doing fast Fourier transform, even on a DSP chip. But when you're doing it, you better be doing it. So you have it powered off, you need it, bingo. My example is the refrigerator. I don't know how many of you follow the American game of football. Unlike your game of football, see, in America, the strong thing about America is we have labor unions. So unlike your game of football, the players don't have to play the whole game. They play half the game. That's their contract. When the one team is on the field that's moving the ball in this direction, which is the offensive team of the other team sits on the bench. And the defensive team tries to stop them from moving the ball. And then they take over, and then the offense goes on the field, and the defense of that second team sits on the bench. And each player plays one half of the game. That's the working contract from the labor union. Except there was one guy back about 20 years ago with the Chicago Bears, and he was called the refrigerator. His real name was what? Nobody. Well, I'm in Spain. I'm not in America. William Perry. Weighed 400 pounds. That's why they called him the refrigerator. He was a defensive player, so when the offense was on the field, William Perry was on the bench, powered off. Powered off. Unless the Bears were this far from the goal. If they were this far, too far, it won't work. But if they were this far, they would stop, they would power up William Perry. They'd bring him into the game. They'd hand them the football. They'd point them toward the goal. Like this. And as I say, this far it works, this far it's too far, he'd never make it. But this far he makes it with the other team hanging over him, trying to get him on the ground. And they finally do after he's crossed the goal line, and the referee says 6 points. The rest of the time the offense was on the field, William Perry is on the bench, powered off. He's functionality that most of the time you don't need. When you need him, you really need him. AMD on their first RISC chip, it was called the 29000. They had an instruction called find first. What that instruction did was the input operand was a bit vector, and the instruction found the first bit in the bit vector that was set. Try to do that in software. Takes you tens of instructions. Do it in hardware. It's a very simple priority encoder. It takes next to nothing. AMD felt that it was sufficiently important when they needed it that they would invest those few transistors to have a priority encoder, do the find first when the operating system needed it. X plus superscalar, I've given you the example of the FFT. The point is that if you break the layers, and if the microarchitect understands what the informatics people need to solve their problem, and the microarchitect can put that into the functionality on the chip, and then the algorithm person can write an algorithm that takes advantage of it, and the compiler person can say, okay, power up the refrigerator, and then several instructions. You don't power up in one cycle. You power up in one cycle, you warp the chip. You can't take that kind of a current spike. But the compiler said, power up. Boom, 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 boom. Maybe 3 cycles, 4 cycles. And now it hands the ball. That is, it hands the data to this very heavy-duty instruction. It gets done much, much faster. We can do it if the algorithm people and the problem people and the microarchitecture people all talk together. But I keep being told, no, abstraction. You got to operate at this high level of abstraction, you know, Java, C++. Java person writing Java code doesn't have a clue what's going on underneath. In fact, my favorite example is sorting. I asked a computer science graduate, does it matter whether all the data can fit in memory, that all the data needed to be sorted, whether it can all fit in memory at one time, or whether you have to keep bringing it in and out of off the disk in order to get the whole thing sorted? And the answer is, of course not. It doesn't matter. So I would invite that student to read Volume 3 of Keynote, where he devotes quite a bit of time to the differences between internal and external sorts. And yeah, matters a lot. In fact, today, it matters a lot how much of that data can fit inside the cache as to what the performance will be. Abstraction is great, but if you don't know what's going on underneath, you're going to be writing bad code. That's not, or designing bad algorithms. That's not me talking. I say that. Donald Knuth says that. You know, my hero in the algorithm business. And it's lots of examples. You want to take a taxi to the airport. So you say, okay, you know, you want to take a taxi to the airport here in town, and you have no idea how to get to the airport. And so you get in the car and in the taxi, you say, I want to go to the airport. And you just start reading the paper, and time goes by, and time goes by, and time goes by, and then you look up and you say, Sagrada Familia. If you don't know the roads between here and the airport, you may find yourself going to the airport by way of Barcelona. You'll miss your plane, and the fare, what they charge you, you won't be pleased with. The scheme chip. You know, back in the late 70s and the early 80s, the guys at MIT decided, you know, maybe there's something to this Meade-Conway. You know, Meade-Conway, that first VLSI design, green, red, must be a transistor. You could design chips without having a clue what was going on. End up designing Mickey Mouse chips. So the guys at MIT, they said, we'll do the scheme chip. They used the Meade-Conway rules. Guess what happened? The chip could be used to make a keychain. And then they said, hey, you know, we're MIT graduate students and young faculty. We know better than this. And so then they went and redesigned the scheme chip, understanding what's going on underneath. What do you think happened? It worked. Sorting, I've already talked about. Database, Microsoft developers. I've got students that I taught in the freshman course, and I will shamefully mention the freshman course later on, briefly. But the freshman course where I introduce students to computing, and they don't get the right programs until after they understand how this mechanism called a computer works. And then years later, I introduced the course at Michigan in 1995. So that's more than 10 years ago. And so I get email from some of these. In fact, my favorite is a couple of Microsoft developers. Are they designing processes? No. They're writing operating system code. And what they tell me is they couldn't imagine being as effective as they are without having learned the underpinnings. Because understanding what's going on underneath is what's needed in order to write better software. Wireless networks. I was just told that these wireless networks guys that are writing the high-level software are now looking at the first layer, you know, the physical layer. You know, where you modulate the carrier, the Poynting's vector, where you actually send electromagnetic energy And they're looking at that layer because in a wireless system, there's things like rain and everything else that can get in the way. And so to write the better software, the better routing algorithm, etc., they have to break the layer. And you know, when these layers first came out, you know, physical layer, link layer, network layer, when that layered approach first came out, it was, nope, you don't break the layers. So even there, abstraction is great, but... So they say, well, you know, if you make me think about these multiple cores on the chip, you know, conventional wisdom, you know why I wrote CW? I couldn't fit the conventional wisdom and have it still fit on one line, and if it would have been too small, you wouldn't be able to see it. So conventional wisdom, thinking in parallel is hard. So that's why we need to not think in parallel. Thinking is hard. What if the programmer understood shared memory, synchronizing primitives? Would it matter? I insist it would. And it would make for much better use of the underlying stuff. In fact, I think the next time, I know, the next time I teach the freshman course, I teach the freshman course every other fall. Next time I teach the freshman course, I've come up with a few programs that I want them to write, and I'll bet that they're going to be able to do it. Maybe because they're freshmen and they don't know that thinking in parallel is hard. They haven't been told that they can't do it. And I came up with about 3 different things. Pipelining in software, where I'm streaming data from one piece of code to feed it the same way I assembly line the hardware. Why not assembly line the data with separate segments of code, which are actually, once you get started, are working in parallel. Factorial. How about if I want to compute n factorial? Let's take a simple number like 10 factorial. I say to you, well, I say to all of you, how would I compute 10 factorial? What would I do? Well, I must multiply. 10 times 9 times 8 times 7. No. I want you to multiply 10 times 9 times 8 times 7. And I want you to multiply 6 times 5 times 4 times 3 times 2. Go. Parallel. And when you give me your answers, what am I going to do? Multiply the 2 and bingo, I've done factorial in half the time. Or parallel search. Why can't I search? Instead of I search like I got binary search. So instead of binary search, I search and I search and I search and I search, and I do it in parallel, and then after the first step, I've got a much smaller segment of second step. If I've got the resources, I can do it in parallel. One of my students, Sanjay Patel, a tenured professor, associate professor now at Illinois, he took 2 years off and to do a startup. And he's a co-author of the freshman book. And I told him about this. He says, you know, you're absolutely right. We do a lot of parallel programming at work, and it never phases us. And why? Because they understand what's going on at the bottom level. One has to understand. There are lots of different ways to do things, and if you don't understand the multiple ways, you'll probably get it wrong. So if you'll indulge me a minute, some of you may be engineers and you actually have a pen in your pocket. You may also have a piece of paper. So if you have a pen and a piece of paper, I'd like you to write down the number 12. Come on, somebody's going to humor me. Write down the number 12. Good. Grab the pen. I'll wait. I've got all night. You may be tired. That's why you had to listen to all this before I get up here. Shame on me. Making fun of the people who make it possible for us to do what we do. Okay, so you wrote 12. Good. Now write 9 under it. Now I want you to add the 2 numbers together. Anybody need more time? Okay. Now I want you to write 378. If you don't play along with me, you're going to miss the fun at the end. Now I want you to write 259. Ready for the hard one? Add those two numbers together. So I've just asked you to do two addition examples. And the answer to the first one, I'll tell you, is 21. How many of you got it right? Good. That's not the hard one. The hard one is, and the answer to the second one was 637. This PowerPoint, I don't remember, you know, this is a new game for me, so I forgot the order that I put these in. 637, how many of you got that right? Great. Now we're ready for the hard one. When you wrote down the number 21 with your pen on the paper, you wrote 21 down. How many of you wrote the 2 first before the 1? And how many wrote the 1 first before the 2? One person, about 3 people. Most of you wrote the 2 first. How many wrote the 6 first before the... Nobody. How many wrote the 7 first? Yeah. So you wrote the 2 before the 1 and the 7 before the 6. That's a little screwy. Not at all. When I gave you the 378 plus 259, you went back to something you learned in the 2nd grade. Or if you had an old man like my father, then you learned it when you were 4 years old before you started school. But he taught you, or your mother taught you how to add. And you know, the way you add these numbers is 8 plus 9. Gives a 7, carry a 1. That's why you wrote the 7 first, because you used that algorithm. But when I asked you to do 12 plus 9, most of you did not do 2 plus 9 is 1, carry 1, 1 and 1 is 2. Most of you went to the table lookup that you had in the brain, said 12 and 9, 21, boom, done. The point is that there are 2 different algorithms. There are 2 different ways of doing it. Is there a right way or a wrong way? No. But there are 2 ways in the microarchitecture. And if the algorithm understands what's below, one can do a lot better. We have an education problem. Top down versus bottom up. I insist on bottom up, continually building on what you already know. Some people, top down. There's a difference between learning and designing. Top-down design is absolutely correct design. If you design something bottom up, what you'll end up with is the old design with a pimple on it. You need top-down design, clean sheet of paper, do your design. But then you already understand the components that you're going to use in doing your design. Learning is different. Learning, if you do top-down, you're memorizing. Memorizing is all learning. You do bottom-up. You do something and then you build on it, you build on it, you build on it. Applications can drive the microarchitecture if we can all speak the same language. If the microarchitects understand what the problems are, and if the informatics people who are not architects understand what's going on below. Since I have the floor, I can't resist at least one slide on education, because, as Matteo says, teaching is the thing I care most about. Object-oriented, which is top first, does not work. It absolutely does not work. Students don't get it. Memorizing isn't learning. In fact, in those university classrooms where you start with C++ or Java, the kid makes a mess because he can't memorize perfectly. Now what does he do? In fact, he gets compile time errors, which to fix the compile time errors, he finds out that he fixes it so the program has no chance of running. And then finally, when he's sufficiently stuck, he goes to the TA. TA looks at the mess, goes, ugh. What does he do? He gets the kid started, does the first half of the program for him, and says, okay, now you finish it. Kid says, thank you. What does the kid then do? Goes to the other TA. Some of them graduate without ever having written a program. Motivated bottom up. Why motivated? Because you got to keep their eye on the ball. So I start up here at a high level. I'm not teaching, I'm just motivating. And then I go here. Still not teaching, I'm motivating. And then I go here and I work up. to here. Then I motivate, then I work up, then I motivate, then I work up. And it works. Students build on what they already know, continually raising the level of abstraction. Abstraction is great if you understand what's going on below. Parenthetically, don't ever be able, those of you that are professors, don't ever be afraid to work the student hard. And those of you graduate students and will be professors someday, same for you. Students can digest serious meat. You don't have to sugarcoat it. You don't have to make it simple. And they won't complain if they're learning. Give them tedium to do, complain all the time. But give them good stuff and serious meat, and they won't complain. And if you do that, you have a chance of educating. There is no substitute for a student or a person designing something wrong because we never get it right the first time, debugging it because they're able to debug it because they understand the lower level, and then fixing it by themselves. One shameful reference to our book, I'll just stick it up there. It's in the second edition. It's been translated into Spanish, and you're all welcome to use it. I said we have an education problem, and I showed you this slide. We don't have an education problem, we have an opportunity. The future chips will have thousands of cores, lots of opportunity for special function units, the ability to power on and off those cores, those function units under program control. If the algorithm and the compiler and the microarchitecture can talk to each other. Here are the layers, and every one of us works at one of these layers. And if we stay within the layer, then we've got a problem. With 100 billion transistors on a chip, no way. Too big a bandwidth problem because of all these cores, too big a power problem. We'll never be able to continue to improve the performance the way we have in the past. Phase 2 of the technology improvement is here. Phase 2 is not going to allow us to keep these layers. Our only chance of continuing the improvement over the next decade is if we think in a holistic way. Thank you very much.
We have time for 2 or 3 questions, please. Any of you like to ask Professor Yates some question? Very clear. Question.
No, they want to see the next event. Thank you very much.
Thank you.
I appreciate the opportunity.
Buenas, ¿se me oye? Buenas. Buenas.
Ah, sí, hable.
Buenas noches. En cuanto